Welcome to this IB Maths Intense session, looking at sequences and series. This is number 4 in the set, and we're looking at geometric sequences in this video, building on what we did in the previous sections on arithmetic sequences. There it is in the syllabus book. Geometric sequences and series is SL 1.3. Very important topic, bound to come up. What is a geometric sequence? Well, when we looked at arithmetic sequences, we found there were sequences that went up or down by a common difference, the same amount each time. But these 4 examples are all geometric sequences. They don't go up or down by the same amount, but they share what's called a common ratio. And a common ratio is a ratio or a number that each term has been multiplied by to get the next term. So in this first geometric sequence, we can see that each term is double the previous term. So our common ratio is 2. In the second one, our common ratio, well, we've halved every term. So our common ratio is a half. And in the third one, we've multiplied everything by -2. We've got a common ratio there. And in this last one, we have a common ratio of 3. Now, in every case, we find that common ratio by dividing a particular term by its previous term. And we can denote that with un plus 1 divided by un. It could be, for example, u2 divided by u1. It doesn't have to be those two, it just has to be 2 terms that are next to each other. So it could be the 11th term divided by the 10th. They will all give us the value of r. And we can also write that the n plus 1th term is always the previous term, un, multiplied by that common ratio r. So we have a good idea here of how a geometric sequence is working. What I really like, though, is to find a rule that allows me to go straight to the nth term. So let's have a look at this example that we saw before. Our first term was 2. And our common ratio was 3. Now, what we've done here, to get our second term, as we said, we multiplied the previous term, which was u1, and we multiplied it by 3, or the common ratio. Let's denote that as u1 times r. Now, to get the next term, I multiplied the previous term, which is u1 times r, by r again. So in other words, it was u1 times r squared. And the third term would be u1 times r cubed, because I'm just multiplying each of them by r as we go along. Now hopefully you can see a pattern here, that if I wanted to find the nth term, in every case I'm multiplying the first term by r to the power of, well, let's see if you can see that. The 4th term we multiplied by r to the 3. The 5th term we multiplied by r to the 4. So, no surprises, for the nth term we'd multiply by r to the n minus 1. And there is a very, very important formula that we need to know for working out the nth term of a geometric sequence. And sure enough, there it is appearing on the formula booklet. You don't have to learn it. It's there for you if you forget it, but it's a nice easy one to remember. So for each of these we can define our rule. So in this first one we've got a first term of 1 and we've got a common ratio of 2. So my rule un would be equal to 1, which I won't bother to write, times 2 to the n minus 1. So this is the geometric sequence of 2 to the n minus 1. This second one, my first term is 1,000. My common ratio is a half. So my nth term rule would be un equals 1,000 times the common ratio, which is a half, raised to the power of n minus 1. And in this final example, my first term is 5, and my common ratio is -2. So my un here would be 5 times -2 to the n minus 1. Nice and straightforward, no tricks in there. Let's have a look at some of the kinds of questions. Some of them will be simple, some of them will be more complicated and might require us to use simultaneous equations as before, or as I'll show you later, we'll need to be using logs because we're trying to solve with exponentials. And if you haven't looked at logs yet, then have a look at videos on solving with logs as a reminder, but I will show you with logs and you can come back to that if you haven't seen that so far in your course. But in this first question, we're told the fifth term of a geometric sequence is 2, and we're told that the ninth term is 1250, and we're being asked to find what values could the common ratio take. So as always, write down what you know. We know that u5 is equal to 2, and we know that to get that we multiplied u1 by r to the power of 4. And we also know that u9 is 1250, and to get that we had u1 r to the 8 equals 1250. Now we have a kind of pair of simultaneous equations here. What we can do is divide u1 r to the 8 by u1 r to the 4 in order to get rid of our u1. You can cancel it down in that division, and that's 1250 divided by 2. So if we do that, we end up with r to the power of 4 is equal to 625. And then we can just solve that as the fourth root. So r must be equal to the fourth root of 625. Now notice that the question said, what values could the common ratio take? So be careful here, because when you take a square root or a fourth root or a sixth root, an even root, then you know that there must be a positive or a negative root, and indeed the fourth root of 625 is plus or minus 5. So the common ratio here could have been 5 or minus 5. Be careful for that, and the question gives you a clue when it says what values. In the next question, we're told that the second term of a geometric sequence is 29,997, and that the fifth term is 1,111, and we want to find the 10th term. So we're going to use the same sort of routine as before. We know the second term, we got that from multiplying the first term, u1, by r, and we got 29,997. We know that the fifth term is u1 r to the 4, and that was 1111. Now I can do a similar division as I did before in order to eliminate u1 from the calculation. u1r4 divided by u1r is equal to 1111 divided by 29,997, and that comes to the fraction 1 over 27. So we know, if we cancel this down, we end up with r cubed equals 1 over 27. So that means r must be the cube root of 1 over 27, which hopefully you can work out in your head. Cube root of 27 is 3, so the common ratio must be a third. But that's not it. It's not just about finding the common ratio. I've been asked to find the 10th term. So now plugging back into the formula, u10 equals, well, I haven't got the first term, so I need to work backwards and work that out. So if the second term was 29,997, u1 must be equal to 29,997 divided by the common ratio. So 29,997 divided by a third will give me 89,991. I need to work backwards because I've got the second term. I multiplied 89,991 by a third to get the second term, which is 29,997. So now I can find the 10th term, which is equal to u1, 89,991, times the common ratio, which is a third, to the power of, was n minus 1, so it must be to the power of 9. And that gives me a result of, well, I'll leave it as a fraction, 1111 over 243. It's nicer as a top-heavy fraction like that. It's a precise, exact answer. A little bit more complicated than some of the early work, I think, on arithmetic sequences. And now let's just look at an example or two where we have to use logs in order to solve. So this time we're being asked to find, this is normally where we're dealing with a solution for n, because it's the exponent and we need to use logs to solve for exponents. So how many terms are there in the geometric sequence 50, 125, all the way up to 4,882. Well, what we can do here is write down what we know. We know that U1 equals 50, and we know that the common ratio is equal to, well, it's 125 divided by 50, which is 2.5. Now I can work backwards, and I know that I got 4,882.8125 by multiplying the first term, 50, by the common ratio, which is 2.5, raised to the power of n minus 1. So now this is about solving n. If I divide everything by 50 to start with, 2.5 to the n minus 1 must equal 97.65625. Just dividing everything by 50 to simplify. Now, laws of logs, hopefully you remember, I can solve this by taking n minus 1 to the front. N minus 1 log 2.5 equals log 97.565, sorry. That's a bit of a mess, isn't it? Let's rub that out so you can see it. Log 97.65625. And that means n minus 1 must be log of 97.65625 divided by log 2.5, which is equal to 5. But that's the solution for n minus 1, therefore n must equal 6. Of course, you could have solved that log equation there by setting n minus 1 equals log to base 2.5 of 97.65, etc. It's just nicer to keep things in base 10. Finally, another one that involves logs. Let's see what we've got here. Geometric sequence has a first term of 7 and a common ratio of minus 2. So we know that U1 equals 7 and the common ratio is minus 2. What term has the value minus 57,344? Now I wanted to show you this because there's a little trick solving with logs and negative numbers. So we ended up here with, well, what do we know? We know that minus 57,344 must have been calculated by multiplying the first term, U1, 7, by minus 2 to the power of n minus 1. Now, I can divide by 7 there to get rid of that 7 from the front. Minus 8,192 is minus 2 to the n minus 1. Now, hopefully you can remember when you're working with logs, logs with a negative base and logs of a negative number, not going to work. So I really need to be working with a positive number here on the left. So if I multiply both sides by minus 2, then I get 16,384 on this side. And you can see that would make my minus 2 now to the power of n, because I've multiplied it by minus 2 again. And minus 2 to the power of n is going to go positive. It's going to be 2 to the n, because I've just multiplied by minus 2. So now I can use logs. N log 2 equals log 16,384, and that's just a nice simple solve like before. N equals log 16,384 over log 2, which equals 14. So the 14th term has the value minus 57,344. Now, you will see with geometric sequence questions a large number of occurrences where you have to use logs to solve. If you haven't done logs yet, don't panic. The video on logs is coming soon, and you'll be able to use that knowledge then to solve geometric sequence questions like these. But I hope that that was a useful introduction to geometric sequences. Thank you for watching. In the next video we'll look at geometric series, where we'll look at the sum of a particular set of values in a geometric sequence. Don't forget to like this video, subscribe to my YouTube channel, IB Maths Intense, and of course, tell your friends I'm here. Drop me an email at ibmathsintense@gmail.com if you've got any comments, any requests, any feedback, or you spotted any glaring errors or omissions that I made. In the meantime, enjoy your maths and take care.